Well, I'm Scott Nolin from the University of Wisconsin Space Science Engineering Center, and I have 30 slides here in 30 minutes, so I'm not going to talk a lot about the background of the center, but here you see a picture of of our building in Madison, Wisconsin, and we're on an isthmus between two beautiful lakes. On the roof of our building, we have a lot of satellite antenna, which we are engaged in satellite meteorology research, and so for our scientists in our building, this is a beautiful part of the skyline too. Not necessarily for everybody, but to them it means you're getting a lot of data, which leads us on to our topic, which is why are we interested in using ZFS for Lustre at Space Science? It's because we're engaged in atmospheric research with the real focus on the satellite remote sensing, which has very large data needs. As our storage has grown, improved data integrity has become increasingly important for us. And the data integrity features of ZFS, which we have some experience with from when ZFS was a purely Sun product. It's an important candidate because of these features. I have a couple of links here. One to a study of the ZFS data integrity claims done by computer science here at the university. I don't work with these people directly, but it's one of the better papers I found online. And next you see a paper from CERN where they're discussing, they did some analysis of with their cluster and some of their storage resources several years ago, and they analyzed how likely it was to encounter data integrity problems, which is important for the type of research they do also. We're also interested in additional features such as compression and snapshots. For example, with compression, I believe Lawrence has achieved, they turned on compression for their Sequoia file system, and I think they're at like 1.8 times, which is impressive. I looked at some of our satellite data, and we're seeing between 1.2 and 1.4 times compression, basically for free, depending on how your storage servers, how powerful they are. And we've been following the ZFS on Linux project at Lawrence for the past couple of years, and that's now in production on a 55 petabyte file system on Sequoia, and so we feel it's Lustre's matured, especially considering that production use. And why we're interested in a test system is we just want to prove to ourselves the concept and validate some design we had with specific hardware, and that also it's fairly new. It has just been released in 2.4. Though documentation isn't there yet, so there's certainly some uncertainty about how to do it and what to do. So it's not the sort of thing where we could commit grant funds for a project that needs storage immediately and say we know this will work. So that makes sense to have a test system. And for the finally, for the best data integrity, we need systems supporting direct JBOD access to disk, and finding the right hardware for that's a challenge. It's a real open question. Our test system, called Cove, which I'll refer to that in this presentation, that equipment was provided on a grant from Dell for this proof of concept. To be clear, this is not an appliance or a supported configuration from Dell, so I think everyone would understand that, but they wanted me to make that explicitly. You can't call them up and say, I'm having problems with my Z-pool. They'll be confused. Now, this test system has no high availability features included. For many of our systems as a research center, we have a next business day support that we provide, the technical computing group, to the center. Sometimes we buy better support than that for our hardware and software, but it's a different environment with a lot of high availability. We do have some future systems possibly coming which will be operational, which may need some of these high availability features. When we built the system and tested it for performance, for data integrity features, and for routine system administration, which are the three topics I'll discuss here, the performance and performance graphs, there's quite a few slides. I just want to say that while this is important, and I probably spent a lot of time on it because it's interesting and it's fun to make these graphs and you want to know how things perform, our focus for performance is simply does it perform close enough to how we expect, not pulling the best performance we can out of it. Data integrity features, which are obviously critical to why we want to use ZFS. and routine administration, which is, my group was responsible for this routine administration of these systems, and so that's where a lot of the pain comes about. If you have the best theoretical system you can build, but you can't maintain it over time, it's worthless to us, really. The system design is largely based on Lustre for Sequoia presentation slides from LUG 2012 by Brian Bellendorf. We communicated with him a little bit to see if we were lining things up about how he expected. The idea is to get a reasonable performance comparison to a known system and some insights into how it might scale. There's no way we can test at the level they did. I have some slides here on details of the systems. I'm not going to go over every detail, but I try to include them all because when researching this topic, you see there's very little out there. So the slides at presentations like these are where you can get a lot of the info. So I tried to put it all in here. In red, you see the main differences. You know, the Sequoia file system has 768 object storage servers. This test system has 2. The metadata targets, they have 40 SSDs. Our example system, we have 4. They use dual RAID controllers and RAID 6 on the controller for the object storage targets. We use JBOD mode and RAID Z2 with ZFS. So for the OST on RAID 6, why are we doing that? So like, you know, RAID 6, we're all used to this. You have a controller, stripes your parity. But for us, it's not the best answer, which is, this is one of the core differences that we have to grapple with. For best data integrity, we want to give ZFS direct disk access. Cove uses a SAS HBA, just straight to JBOD mode disks, and you create a ZFS RAID Z2. As far as the data protection goes, it's, you know, same idea as RAID 6, software RAID 6 basically, but it's called RAID Z2 because it's from ZFS. For our design, this also allows us a little bit of advantage with our particular hardware we use, that we could stripe across enclosures. So we could lose an entire enclosure and keep operating, which is important considering we don't have a high availability design here. And so there's no SAS multipath, you know, so we want things to be actually directly attached individually is an advantage for us. So the question gets to be, I think when we were discussing this design a little bit with Intel, this even came up, why no RAID Z2 on Sequoia? Communicated a little bit with Mr. Bellendorf, and he explained that the, you know, Lawrence, at the time, this was a couple years ago, they needed something which would be used for ZFS or LDISC-FS, and they used it as a risk mitigation strategy because it's the first Lustre ZFS system. Since that point, they've developed a lot of confidence in their implementation, and they expect future deployments to be JBOD based, so they're going to face some of the same issues we're facing. Here's just a layout of the hardware configuration with some details. Probably the biggest difference, or the most important thing to look at here for our test system is you see a lot of lines for SAS cables. This is literally 5 SAS cables from each object storage server going to each MD1200 disk array, which is a 12-disk 2U array. It's not particularly dense. For us, it works well for the scale systems we use. Probably hard to see. These are in split mode. There's a little dotted line down them. You have a switch on them, so it's unified with 2 controllers, or you flip the switch, and it's just like you have 2 small 6-disk arrays. This allows us to achieve the OST to OSS ratio that's the same as Sequoia, so we can do some reasonable comparison of performance. And once again, because of how we've laid it out, we can lose an entire enclosure. I tried to color code the disk, so you see, like, you know, OST 0 there is in the blue color, and OST 2 is in gray. Pretty simple idea, but it works well. Here's a detail on the MDS system. You know, Sequoia, they have an HA pair, and for this test system, we just have 1. And the big difference being you have the 4 disks. Now, in this case, for the MDS, Dell had Dell's RAID card, their H310, which is their small internal RAID card. You can turn that into direct access mode. So we didn't have to do anything quite as exotic as you'll see for the external stuff. The OSS unit in detail, I won't go into the the whole list here, but the storage enclosure connections, you'll see the Sequoia system is, I think it's a NetApp, and it's a direct InfiniBand connected in HA pairs. Ours is not an high availability. It's with the simple LSI SAS 8-port connector. The OST units, once again, the big thing to note is, the RAID Z2 versus RAID 6 on the controller. We have, the density obviously isn't as high either. For software configuration, this is just to show what we tested against. On our servers, we had Red Hat 6 and Lustre 2.4 for ZFS. With the 2.40 release, we pretty much loaded up as soon as it was released. ZFS has gone to 0.62 since then also. For our LDiskFS tests, which we ran, and you'll see some of them, but not for all of it, because the configuration is not quite as possible to be exactly the same. But for that, we ran it on Lustre 2.3 because 2.4 wasn't out. These are all built with the OFED Mellanox stack. Since then, last week, we've been working with the patchless kernel. With ZFS as a backend, you can use a patchless kernel for the server too. Haven't tested it yet, but we just got the file system mounted last week. So that's a very attractive feature for us. Just with day-to-day administration, having a kernel that you don't have to build by hand is a big deal for us. So we were ready to go forward with 2.4 everywhere because it is compatible to all our versions of Lustre in the building, back to 1.8 series. And we'll have to have a little bit of cold water thrown on us with the 2.5 upgrade. And I understand why we do it, but for us it's kind of a bummer. But here's, and our test clients are Red Hat 5. We only have 4 because this is all tested against, we don't have a big test system. This is an active cluster being used. And that is on Lustre 2.15. Our next test, we'll actually be able to test on some 1.8 clients too, which will be interesting. But so for metadata testing, we ran MD test. We used our 4 clients with 64 threads, and what I see from Sequoia was they had 52 clients. They're 40 disk mirror. One problem I have with MD test is perhaps if you look in the code, you can find what the units are explicitly for your output, but it never tells you, it just spits out numbers. But it's IOPS, I hope. So file create and remove. You'll see here in the graph, we've got the blue shaded bars are our test system, and the red is Sequoia results from the LUG 2012 graphs. You'll see, the biggest bar is, LDiskFS on Sequoia. Similarly, on ours, our LDiskFS test, which was a RAID 5, by the way. It should have been RAID 10, but that's what we tested on. That's the best performance. This is a known weakness of ZFS currently as a backend for Lustre, and that they expect that to improve. The big question we're asking ourselves at the center is this good enough for our performance? Then on file stat here, I think you see where the 40 SSDs really are an advantage. Now with our 4 SSDs, we don't see a huge difference on file stat between LDiskFS and ZFS. I assume that's just because we are bound by something besides, because we only have 4 disks. So in conclusion, the performance seemed consistent enough with Sequoia that I think that our configuration is sane, and stats much lower. The metadata performance for us is acceptable, but this is something to consider if you're looking at CFS as a backend for your metadata servers. Next, we looked at I/O performance with IOR. Once again, the biggest difference here on our benchmarks is our RAID Z2. The information I found here was from Andreas Dilger's 2012 LAD presentation Lustre on CFS. Very conveniently, the slides on a 2 OSS example. They had run 1/384th scale, which is funny. Other big differences there was Stonewalling, ours is not stonewalling test. I don't think it made a huge difference. And here we see the reads. Note that the scale on the bottom for number of nodes on Cove versus Sequoia, ours is linear, theirs is not, because they have a lot more nodes than we do. Mainly what we're looking at is over out at the 4 line there. You'll see, are we somewhere reasonable with their performance? For writes, similarly, it looked about right. I mean, with 2 OSSs, I think what the Sequoia test suggests is your scaling stops until you get more OSSs around 2,500 megabytes a second or more. And one thing that we noticed, though it's not particularly important for our usage, is that with 1 node, it seems like maybe because we have a newer version of Lustre and ZFS, maybe there have been some improvements in single client multi-thread performance. So over at 1 node, there are some that are a little higher. Really doesn't matter that much for our use case. It's more like right around 3. In conclusion, it seems the performance compares well with Sequoia, and we assume it'll scale similarly, though we won't be able to test to that level. We will be able to test a slightly larger scale soon. Next, we get to the data integrity test, which is really the focus of why we want to get involved with the ZFS file system. So we tested all the normal stuff, like replace a disk, system goes away, or an OST's offline. There were some unplanned tests, as I was doing a lot of the testing on this hardware, and my role is, half of what I do is management and meetings with the university and our collaborators. So after a long day of slaving away over PowerPoint and a meeting, it was kind of nice to get back and test some stuff, but I'm probably a terrible admin for that sort of stuff because I would make mistakes and turn the wrong thing off or something, and so there were some unplanned bad admin tests, and we also, it worked well. In all cases, we didn't have any problems with losing data, and striping across the JBODs meant we could turn off an entire enclosure and keep running. So you can lose 12 disks, but you can't lose 13, or you can lose 3 in the wrong order and you're in trouble. And the really important for us data integrity test was corruption testing. For this, we took some satellite data from the VIIRS instrument on the SUMI NPP polar satellite, which is the latest polar orbiting satellite to go up. This produces about 1 terabyte of data a day, which is being stored at our center for a project, and they generate MD5 sums for all of it, so this is very nice for testing our data integrity. So I took this and stored it on Cove, verified all its MD5 sums, and then did some damage to the disk simply by, nice thing since this is not hidden by a RAID, you could just DD to the disk directly and at random, wrote random data and corrupt it. So you can simulate the kind of data corruption you can get that a lot of RAID cards, most RAID cards aren't going to necessarily detect. Or if they detect it, they're not going to fix it for you. And so running a zpool scrub and repairing it and verifying the MD5 sums, no data was lost. So that's an important one for us. Data corruption does happen. We had a file system with some corrupted data just last week. I think it was an XFS file system. Really the worst part of your data corruption problems to me is people ask for a certainty of which of my data is bad, even saying, well, some of it is, can't even tell you the state of the rest of it. It's a problem. So finally, we'll move on to system administration tasks, which is where we have to actually implement this stuff, because we were not developers, we're administrators. So we're focused on making it work day to day in production. So while giving ZFS these direct access to the drives is the best choice for the data integrity, this leads to some real system administration challenges. ZFS does the volume management in this case, so functions of volume management typically are provided by your vendor's RAID solution. These aren't available. For administration, ZFS snapshots are a really nice feature for metadata backups. We know about ZFS snapshots from our use with it before. But there's a lot of things you can use them for, but for metadata backup, it's very nice. And we tested various tasks with reasonable solutions for most, but the firmware updates are really a concern. Next, I'll show a grid of various things we did. On the far right here, you'll see the H810 RAID LDiskFS. This is our traditional method. That's a RAID card. And how you do all these tasks, like identifying which drive has failed, obviously important when you're going to replace it. Updating the firmware, important if your vendor says, well, is your firmware up to date, which is the knee-jerk reaction for hardware failures. Same for the enclosure. Notification that the drive did fail, predictive failure, the metadata backup and recovery was the main task we covered. So if you look on the right, you see the more the traditional method, which is, we use the vendor tools or the vendor utilities to do pretty much everything, and metadata backup and recovery is with DD or TAR, depending on a version of Lustre. In the middle, you see the H310, which is a pass-through mode on the metadata server card. So this gives you direct access to disks, but a few more of the vendor features. The main thing that's a little different there is the drive identification. The ZFS distribution in Lustre provides, or just Lustre in general now, provides vdevID.conf, which lets you make basically make an alias path that's readable. So we map the SAS path to a name that makes sense to us, like enclosure 21 slot 3. So when a drive fails, they're enumerated, and that also helps you with your, locating them. And then you'll see, in that case, the rest of the stuff like firmware, it all updates it fine because it's vendor supported directly. Now for the OSS OSTs, drive identification's done the same way, though you can't enumerate the drives and light up the drives and identify them because OpenManage doesn't know about them. So we use LSI command line tool. There may be better, more generic ways to do it with direct SAS commands. We haven't had time to look at that. You'll see the firmware is all in red there. That's the worst part, how you actually update the firmware. Predictive failure, Smart CTL can do this for you. And drive failure notification, zpool status results. That's nothing new. If you've worked with ZFS before, that's how you detected failed drives. There's plugins for Nagios that are 8 years old that we just used, and they directly work. So on to the topic of the firmware. So the Red Hat, what happens is the Red Hat utility from Dell identifies, it does see the drives. I assume it's just using a regular SAS command. But it fails due to checking the logical drive status, which means it makes sense. It wants to talk to what their supplied H810 RAID card, see what's up, but you can't update it. So in order to get firmware updated, you have to bring the system down, put in an H810 card, recable it, and flash the firmware. Now that worked, and it didn't do anything terrible to the drives, like write a UUID to the disk or confuse ZFS. But obviously it's awkward and slow due to recabling, and we can do it. For some systems, like our disk archive that's upcoming, it's even acceptable because they can take a day or 2 or 3 or even up to a week of downtime. It's probably more like a day to do something like this for something with maybe 30 enclosures. Obviously, that's not going to scale to 3,000 disk enclosures. Though to be fair, if you have a massive installation, the 12 disks per 2U might not be dense enough for you anyway. Enclosure firmware, we didn't test this. Now these enclosures we've used from Dell, there have been 2 or 3 generations. There's only been 1 firmware upgrade. I assume it would be the same situation though. Now for metadata backups, we use ZFS snapshots. There are object type backups. You can't do file-based type backup, meaning with TAR, for ZFS file system currently in Lustre. I believe you may be able to in the future. It's not important for us because the snapshots work really well for that. The biggest problem with doing this is just, once again, the documentation isn't quite there yet in the Lustre manual or man pages, but you can certainly do it. Now, in conclusion on system administration, the main point here is while giving ZFS direct access to drives and JBOD is really ideal for data integrity, it does introduce some problems. These, I believe, the root of this problem is that just the vendor tools are focused on the RAID controllers. An enterprise solution is get the best, high-end RAID controller you can to handle all these disks. The ZFS technique of doing it all in software is really, you want it to be as simple as possible so that ZFS can repair failures on the drives. Like we like to say that you have this talk about this idea of predictive failure or pre-failure mode. Like to me, disks are failed, or they're in pre-failure mode, or they're in pre-failure mode, which is you just bought it and it's going to fail later. So most missing pieces here can be replaced with Linux tools directly. Firmware updates, though, they definitely need some work. Also, ZFS snapshots, they're very convenient for metadata backup and restores. Where are we interested in going next? Well, we do have the disk archive system, which contains all of the geostationary satellite data over the United States since forever. Actually, the first weather satellites for meteorology were designed and launched by our center, so we have a history of this stuff, and we've been in the National Archive in the past. Now we're not, we are still an archive, but so this is a system that's in production. It's in production supporting research, so it doesn't have strict high availability requirements, though. With this system, we will try high availability metadata servers. We're going to try ZFS, and we're going to use InfiniBand SRP mirrored LUNs to do this based on Charles Taylor's presentation on the same. So that should give us, even if we don't use active failover, we may use the technique with making the failover more manual, so it doesn't automatically like power down the second node, because we don't need that kind of uptime. We just need assurance that our metadata is good. We will also have metadata backup. So we'll try that out. There's obviously some system administration work. We're pursuing firmware utility improvements with Dell. Really, the blocker there is really minor. If we could get access to the source of the code, we could fix it. You know, the guys that work with me, my staff, of course, their first thing is like, well, we'll just patch the binary and get that to work. I'm like, you could do that, but I'd rather have have a solution provided. So we'll see. We'll see how that goes. And we have a lot of work to do on administration, setup, and monitoring documentation. And we will complete that and make it public one way or another by the end of 2013. I'd like to thank Brian Bellendorf at Lawrence. Obviously gave us a lot of critical advice and made us confident in going forward with the design, because we wanted to be able to compare it to their system. Jesse Stroik and John Lannon at SCC. Pat Myers and Andrew Waxenberg at Dell, who are normally used to trying to get us to buy things. You come to them and say, give us something for free. It requires a little bit of different thinking in the Dell HPC group, which helps make that happen. So if anyone has any questions? Yes, sir.
Can you test the system in failure conditions? So if you have a bad disk drive, so what kind of performance hit do you see?
Under failure conditions, what kind of performance do we see?
Yes.
We did not do IOR tests with a disk drive failed. It'd be a good one to do, though.
I have actually two questions. First
Yeah.
questions, how many hard disks did you put in a Z-pool? So basically like Z-pool crate, and so how many Z-pools you had?
Each, how we did it is and we'll put out even more detailed documentation when I get a chance by the end of the year, but each OST is a Z-pool, which is, I think, the sort of the recommended way based on the scant evidence I could find online how to do it. So it's, you know, each Z-pool is 8 plus 2. So each OST is a Z-pool.
And the second question, how do you solve the problem that ZFS for Linux currently have no mechanism if you have a spare disk? The spare disk will not automatically kick in if you like have a disk failure. While you have a hardware RAID, of course the spare disk will kick in. So did you run any cron jobs?
With our RAID Z2 with 2 active parity disks, we just don't have a hot spare. So you can lose 2 disks and that's it. So it's not hot. You can take it out hot and put a new one in, but we don't have hot sparing in this design.
Okay.
What else? Oh.
So can you test it this email?
Yes. It takes as long as it depends. The time is going to vary on, I didn't time it, and I don't have detailed timings, but the time varies depending on how much data you have written to the disk, because it doesn't have to read, unlike with the, or at least with the RAID cards we're used to dealing with, it has to read the entire disk. The rebuild time is that. The rebuild time is, now I have not corrupted an entire disk, we haven't filled an entire disk to see what it would take to rebuild the whole thing. So maybe it's not as good if your disk is full. But certainly in the case where we had 20 terabytes there out of like 120, the rebuild time is faster, I believe, than with a RAID failure, because you just have to read the portion of the disk that has data on it already. So we certainly haven't tested for every sort of problem you would have in an intense, high performance, high availability situation. And by the way, anyone's welcome to talk to me today about this stuff after me.
Sorry for my third question.
That's okay. That's
just
okay.
Curious. Did you also had any like performance measure in terms of CPU load? Because ZFS is, if you just have like a lot of I/O, or you have to re-silver your disk, and usually the CPU load goes up. Do you have any graphs or
I don't have CPU load graphs. I mean, we looked at the CPU while we did various tests, including the IOR tests. Part of the reason we mimicked the Sequoia layout was I could not spend as much effort on that, because I assumed that they bought enough CPU and memory to handle it. I didn't see any problems, both with the IOR test, and actually I didn't mention, but when we ran the MD5 sums on everything, we ran that as a cluster job. That was actually another nice test of real world. When you're running MD5 sum, you're reading all the data. You're reading everything, which is certainly worse than writing. And so I looked at network load and CPU load and stuff while we were doing that, and it was okay. Though CPU load under rebuild would be an interesting thing to see, though.
Did you look at performance without clients in the picture, say with OBD filter survey or anything like that?
No, we did not.